Hello, students. Welcome to the Fundamental Physics Lab series. And today we're going to talk about the Lab-Sound-02, the resonance of sound waves. This is part of the lab offered by the Department of Physics and Material Science at Chiang Mai University. So today we're going to talk about sound waves. So whenever we make sounds, um, literally our throat just make the vibration in the air, and then that vibration creates wave through compression and the retraction of the air. So this vibration allows the wave and the energy that you're creating using your throat to be able to travel through a medium. And then if you trap the compression of the air with time, you can see that certain part of the air is going to be pretty dense, and some are going to be pretty loose, and going to be dense again. So the distance between these two dense part is called lambda, which is the wavelength, and then the frequency at which your source is vibrating, in this case like your throat, it's gonna create the frequency at which the sound is gonna cause the oscillation. So here, um, we can actually use the relation of the frequency multiplied by the lambda to calculate the velocity of the wave. And and then again, from our theory, we know that the air sound velocity is also dependent on the temperature. So if we know the velocity at 0 degrees Celsius to be 331.5 meter per second. So if you measure the temperature in Celsius multiplied by 0.6, you should get a rough estimation of the speed of sound in the air. Um, that should match the theory if you multiply the wavelength with the frequency, because wavelength is how much a wave is traveled in a wave period, and then this is how fast a period goes. So literally, if you multiply these two, you should get a speed of sound or speed of any given wave um, in meter per second. So then again, so today you're going to be comparing these two values in order to figure out what is the frequency, what is the velocity of the wave in the air. So in this lab, we're gonna be measuring the resonant peaks. So literally, if you use a source and and then the source is gonna create wave that travels here, and then once it bounces back, it's gonna hit the source again. So literally, if you have like this pipe that has a variable height, you can actually generate the resonance. So resonance happens whenever the crest of the wave hits the bottom and then it comes back. So peak to peak, it's gonna constructively interfere. And then again, if you go further, you're gonna have another form of wavelength that actually has a constructive interference. So in this case, we're gonna be measuring these two modes. The first mode is 1/4 the wavelength, and the second one is 3/4 the wavelength. So how can you determine this? Is like this from here to here is called a node, where the vibration is not allowed because it's hitting the surface of the water. So to get a proper vibration, you cannot have like an oscillation here constantly because the water is going to absorb it. So the standing wave mode is the self-sustainable mode. So right here, you're not supposed to have any vibration, and right here, you're not supposed to have any vibration. So this is half a wavelength. So this right here is a quarter of a wavelength. So therefore, um, each time you hit this specific value, if it matches the wavelength of the traveling sound, you have what you call the resonance, where this part of the tube is gonna be very, very loud. And as you move the water down here, you can actually change the height of of the pipe that's actually working as your close-end pipe. So, and by using a tuning fork hitting on the top, you can generate a constant frequency onto this thing. So if the height does not match the lambda, like say the height is here, you're not going to generate the resonance. So the sound is going to be really quiet, and then it's going to be really loud once you hit the 1/4 lambda. And then as you reduce further, it's going to get quiet again, and then it's going to get louder again once you hit 3/4 lambda. Okay, so in this lab, we'll be finding the 1/4 lambda and the 3/4 lambda. So where F is the pitchfork frequency. So pitchfork is like a tuning fork, so it is supposed to produce like one singular frequency that is being resonated in the tube, and then lambda, you can actually calculate it from the L1 and L2, which is the height at which you hear the loudest noise. So the first time you hear the loudest noise, you call that L1, and the second time you call that L2. So you know that L1 is 1/4 lambda and L2 is 3/4 lambda. And then, so once you know L1 and L2, you can figure out what lambda is, and you can, since you know the frequency of the tuning fork on the first part, and on the second part, you'll be finding this frequency. So by knowing the frequency and knowing the lambda, you can calculate the velocity, and then you match this velocity with this velocity and see if it divided from one another. All right, so you compare it with this number. Okay, so the lab tools you're going to be provided with um, a tuning fork, and then this hammer to hammer down the tuning fork and then create the vibration here. So here's an example of how the lab is done. So basically, you hit the tuning fork and then you adjust the level until you hear a really loud noise. So right here is supposedly the loud noise, and then you measure this height, and this height is going to be your L1. Once you figure out exactly where the L1 is, and you can just start reducing the height all the way to L2. So you keep hitting the tuning fork, and then you should be able to hear how far it is that you have like the second resonance mode, L2. So the first, the L1 is going to be 1/4 lambda, and L2 is going to be 3/4 the lambda. Okay. So first part, you're supposed to find the velocity of the sound. So you measure L1 right here and measure L2 right here. And then once you measure L1 and L2, you should know what is the lambda. And then once you know the lambda, you can calculate the velocity by multiplying F and lambda, and then compare it with theoretical value that you can obtain by measuring the temperature of the room, and then use this formula to estimate the velocity of the air, the sound in the air. Sorry. All right, and the second part, instead, this time you'll be repeating the experiment, but you'll be using two pitchforks, which actually have different frequency, and you're supposed to determine the frequency. So again, you repeat this experiment twice with the pitchfork number 1 and pitchfork number 2, and then measure L1 and L2 again. So for each pitchfork, you should have different L1 and L2 that gives you the loudest noise, and then from there, once you know L1, L2, again, you can find the lambda, and then you can calculate the frequency by, this time, calculating frequency by using the velocity you obtained from the first part divided by the lambda that you have right here, because V equals F lambda. So if you divide the lambda here, you get F equals V divided by the lambda. And then on each pitchfork, you're going to be given what is the frequency of the pitchfork. So compare the frequency of the two, compare these two numbers, and then you should be able to estimate what's the error. All right? Okay, enjoy the lab, and thank you for your kind attention.